Hi, hello, welcome to section number 9. Our next to last section, next to last content section at least. Um, Wild Times at Sweet Valley High. Um, so, lecture 9 was all about like benzene stuff, so EAS reactions and aromaticity and all of that. And in the version of section of this in the summer class. There's a whole other topic that's taught in this lecture that we skipped. And so I have a little bit more time than I normally do for this section, which can make up for time that I did not have for some of the other sections. And so I want to spend a good chunk of the last part of section just talking about some more study strategies as y'all kind of head into the final the final midterm exam and the final exam itself. Just to give you some more kind of ideas for studying. But with that, anyone have anything that they want to touch base on? I'm also supposed to ask you how you feel about getting the median grade released, which I don't know, it's my philosophy that I think that we should always release like distributions of scores and information like that to students for like transparency reasons. But is that something that y'all like, or is that something that people don't care about, or the class isn't curved, so it's kind of whatever, but work. Any other thoughts from folks on that? Slay. I had another thing. Oh yeah, mid-semester meetings. I started meeting with people yesterday, and things have been going well. There are still several slots left, so you should have gotten a sign-up from me via email that has a link to my Calendly to like sign up for 15-minute meeting slots and stuff. I still have some slots available over the next week, so if you haven't signed up yet, feel free to, or if you want me to send you the link for that, let me know. Send me an email about it. But without further ado, let's talk about some benzene things. So, the overview here is that our last kind of family of reactions that we are learning about in lecture 9 is the family of electrophilic aromatic substitution reactions. So the whole purpose of these is to add something onto an aromatic ring, and we, for the purposes of our class, pretty much exclusively use benzene as our aromatic ring of choice. So aromatic rings, because they are so stable, they are not very good nucleophiles. We have our benzene ring with its double bonds and everything, and the electrons are doing resonance. They're kind of going round and round in their little electron hamster wheel. They're very happy. And so they don't want to go out and attack something. They don't really want to be a nucleophile. And so in order to get benzene to react with things, we essentially need to make amazing electrophiles. And most of the electrophiles that we use for these reactions are so volatile that they aren't like shelf stable. They aren't something that can just like sit on a counter for a long time. We have to form them in situ, which means like we are mixing two things together and then they form the like high energy electrophile. Or I guess it would be low energy electrophile because we're lowering the energy of the LUMO. Maybe I'll say the reactive electrophile. The mechanism for EAS though is actually quite easy. It's only 2 steps. So, oh, sorry, I'm looking at the chat. Yes, I think y'all are figuring it out. But in order for aromatic rings to do this, we have a really good electrophile that's formed in situ. Our benzene ring goes and attacks it. And when we do that, we actually break aromaticity. So the ring is like no longer aromatic at this point. So then we already had one hydrogen at the position where we added, and now we've also added an electrophile at it and a carbocation. This step is kind of reminiscent of like an alkene reaction where you make a carbocation after the first step. And then the important thing is we have to restore aromaticity. So what we do is we use some sort of base, something in our solution to go and deprotonate this hydrogen, fold back in, make a double bond, and then suddenly it's a aromatic ring again. And so at the end of the day, we've kind of substituted one of our hydrogens for an electrophile. Hence, electrophilic aromatic substitution. Blah, blah, blah. So, we have all of these electrophiles, and they kind of fall into three families. The first family is halogenation. The second family are adding these deactivating acids. And the third family is called Friedel-Crafts, and it's for adding carbon-based things. So let me jump over to the web for this. So for our first family, Br2 and Cl2, if we want to add a bromine or a chlorine, it's essentially like we saw that alkenes could do this with just bromide and just chloride. But because our benzene is not as good of a nucleophile, what we need is something that acts as a Lewis acid. And that's going to be this FeBr3 and AlCl3. So what happens in our mechanism is a lone pair on the halide goes and attacks the metal, or iron, or the aluminum, each of which have an empty orbital. And then the nucleophile can then go and attack the other side bromine, and then the rest of the molecule just becomes an excellent leaving group on its own. We know that halogens do not like to have a positive formal charge, and so it actually does want to break one of its bonds fairly easily. So that's kind of the general strategy here for the halogenation reactions. Then, moving around our clock, we have adding a nitro group, NO2, and adding a sulfonic acid here. So for both of these, we are using sulfuric acid with a combination of something else, either nitric acid here or sulfur trioxide. Now, both of these are pretty reactive conditions to subject a ring to. Essentially, we're kind of boiling it in acid in order to create something reactive enough for the reaction to take place. For nitric acid and adding the nitro group, the electrophile that we want is this long, slender boy NO2 plus that is actually linear orientation. And in order to get there from nitric acid, HNO3, we need to kick off an oxygen. And the easiest one to kick off is going to be the one that's already an OH. So first step is we protonate it with our H2SO4 acid. And then we do a lone pair push kick off water as a good leaving group. And now we have our excellent NO2 plus electrophile. For sulfuric acid, for adding the sulfonic acid group, all we do is take our sulfur trioxide, which I always think is kind of fierce. She's just so symmetric. And then you protonate one of the O's, and then that's going to make this pi star a good acceptor for the benzene ring to come and attack. And the benzene ring attack, just to kind of abbreviate it, I just put it as nucleophile attacking. I put a lone pair. But really, in each of these cases, the nucleophile is benzene, and the donor is the pi CC on a benzene that's going and attacking. So these are our kind of deactivating acids group. And then our last group are Friedel-Crafts reactions. So both of these typically use something with a chlorine on it, either an alkyl chloride or a acid chloride here. And they use the Lewis acid AlCl3 again, trend alert for these reactions. And basically, we are trying to make a really good carbon electrophile. Now, we've already seen one really good carbon electrophile, which is a carbocation. So, the way that this strategy works for Friedel-Crafts alkylation, if we just want to add straight up carbons, is our alkyl halide, the chlorine, is going to associate with AlCl3. And then this Cl and AlCl3 is just going to straight up leaving group leaves and creates a carbocation. Because this method relies on carbocation, we know that carbocations are only going to be really available to us and have this leaving group leave step if we have a tertiary or better carbocation, like a resonance stabilized one. The other one that students often forget of a way of making a carbocation is we can make it from an alkyl halide, typically like a tertiary or resonance stabilized alkyl halide. Or we can have something like an alkene with H2SO4. So, ding dong, attack a carbocation. It's slightly harder if we want to put a carbonyl onto a ring. So if we look at the schematic over here, the line reaction, what we have is we take an acid chloride, and essentially the carbonyl and the R group on the other side both get added to this ring. So it's almost like we're doing kind of like if you just looked at the line reaction and knew nothing about the mechanism, it would kind of look like a CAD reaction to go from like a acid chloride to a ketone. The way that we make the carbon in our carbonyl, because this carbon is the one that's going to get attached to the benzene ring itself, the way that we make that into a really strong electrophile is by making a CO triple bond. And she has a fancy name that I'm forgetting right now, but I actually might take a second to look it up really quick. So a CO triple bond is called what? No, it's not popping up. So the thing is, she has like a government name and she has like an informal name, and I remember the informal name. The informal name, we call it a carbonylid, I think. I don't remember anymore, but just she's a character anyway. So what happens is the chlorine associates with the AlCO3 exactly like we've seen in so many of these steps before. We associate with Lewis acid, and then we have a good leaving group. So what happens is our oxygen is going to push down and make a CO triple bond and kick off our leaving group. And then now we have this really good pi star CO electrophile that's going to be even better and even higher energy than just a typical carbonyl. One reason for that is because we have a positive charge on the oxygen, so the positive formal charge lowers the energy of the LUMO. And then the second reason is because the more pi bonds that we have in place, the easier it is going to be to break one of them. So we do kind of a typical like carbonyl attack from the benzene ring. So that's kind of like a little overview, just talking through some of the details of these mechanisms, just to kind of see it again for a second time since the lecture. But any questions on that so far before we jump into kind of next steps? With a triple bond, is it still called a pi bond? Yes. So triple bonds are made up of a sigma bond and two pi bonds. Because like bonds for the purposes of our class can only be classified as sigma or pi. Like they're like a double bond or triple bond, they're just made up of combinations of sigma and pi bonds. I think there's also like a delta bond or something, and that's like with d orbitals. But maybe I'm just like not remembering words today, so I might be spitting like fake news, like Colton's individual science here. So take that with a grain of salt, but there we go. Now I have some practice here, but they're just here because of like the way that the page formatting worked. So we are actually going to come back to this after we talk about the second part. So like you are mostly going to be doing these EAS reactions. For line reactions, they have a lot of things going on with them, which we're about to talk about. And then for the mechanisms, I would say the Friedel-Crafts ones are the ones to be most familiar with. I think that those are the ones that appear in the most problems, exam level problems, and that we can ask the most kind of theory questions on. But if we are adding these reactions to a lone benzene, like a naked benzene, then the reactions are boring and they're textbook. But we have to start thinking about, what if our benzene is substituted? That brings us to our next little section on directing effects. So, I remember learning this for the first time in spring 2016 in OChem 2, and Beyonce's Lemonade had just come out. And I was learning these reactions in a coffee shop. I got there at like 10 a.m. and then I left at like 8 p.m. And I was there all day listening to Lemonade on repeat and learning this. And the way I remembered this, the fact that if we have some group on a benzene, the positions next to it are called ortho. The position opposite's para, and the position in the middle of it is meta. And because Beyonce's Lemonade was in my head and that general kind of imagery, I saw this and I said, romp, like a romper. And I just imagined Benzine wearing a cute, like, little, like, romper. And, like, Benzine, romper, romp, your R group, ortho, meta, para. It's kind of dumb. That's the way I learned it. But I don't know if that's helpful. And this is always based on where the R group is. So if you place the R group over here, suddenly the ortho are the ones right next to it over here. Para is opposite of it over here. And so it's not like an absolute position because we can rotate these benzene rings. So, quick pop quiz. What's the relationship between W and Y? Para. W and Y, para. What about X and Z? Ding dong. X and Z, they are meta to each other. Meta, the relationship is also like skip one. And then what about Y and Z? Ortho. Very nice. So, with this, I'd like to revisit an icon, if you will. So, if we have a benzene and a carboxylic acid, her name is benzoic acid. Okay. Then, if we add an OO single bond, this now, like an OO bond is, we refer to it with peroxy. So, like, hydrogen peroxide looks like this, HOOH, with that OO single bond. So now we're at peroxy benzoic acid. And if you put a chlorine here, these are meta to each other. This is now metachloro peroxy benzoic acid, otherwise known as MCPBA, my favorite reaction or reagent in OChem 1. So, like, again, it was kind of weird when we did the reaction for lecture 8 and we just said MCPBA as like word vomit. But it comes from the M-meta naming that we have here, conventions for benzene, these relative positions. Ding dong. Okay, so let's talk about substituted benzenes going into reactions, which is kind of the setup that I had done before we did this little relative system. So if something is on our benzene, there are two questions that we have to ask. One question is a question of activation. So, does the group that's on the benzene ring make the benzene ring more likely to do EAS reactions, or does it make it less likely to do EAS reactions? If we have an electron donating group, that's what this EDG abbreviation is for, electron donating group. Electron donating groups push more electrons into the ring, and in our EAS reaction, the ring is what acts as the nucleophile. So if we're pushing more electrons into the ring, it's going to do a better job of being a nucleophile. So we say it makes it more reactive to EAS reactions. Whereas an electron withdrawing group, so if we have our benzene ring and we are pulling electrons out of the ring with some substituent, then our ring is going to be less likely to go and do some sort of like nucleophilic attack because it just has less electron density in the ring. Then the second question that we have to ask after activation is direction. If we have one thing on the benzene, how is that going to affect where the next thing is added? And this is what we call directing effects, and directing effects are controlled by resonance. So, kind of separating this out into a couple key facts. Electron donating groups are activating, which we already said, they push electrons into the ring, and they direct ortho and para. So if we did out all the resonance structures here, or the major resonance structures, for this is aniline, benzene ring with an NH2, here, what we see is we are kind of bouncing around a negative charge on the ring. And if we look at what positions the negative charge lands on in our resonance structures, they are landing on the ortho and para position. So, relative to all of the carbons in the benzene, the carbons on the ortho and para position have a little bit more electron density on them, and so they are going to be the ones that are better donors. So if we have an electron donating group, it's going to direct the addition of the next group added to ortho positions or para positions. Now, here we had electron donating groups donating via resonance, but we can also think about alkanes as being electron donating groups. And the thing that's kind of tricky that comes back is this word that we've mentioned a few times now, hyperconjugation. That is what we said was kind of a sigma bond donation that is much less significant than resonance. It's a much milder kind of donation here. But it still is going to direct things ortho and para, even with that milder donation. Now, if we have ortho and para as options, you might be like, what if we want to just get one molecule? This is more kind of FYI. I don't think that there are a lot of questions that actually ask y'all to deal with this, especially on the problem set. But typically, if our group that's on the ring is not that bulky, let's say we just had a methyl group, you're going to get more ortho than para because you simply have two options for ortho and one option for para. So that's 3 choices, and you have a 2-to-1 ratio here, roughly. So typically ortho is favored, but if you had a really bulky group as your R group that's already on the molecule, that is going to strongly disfavor the ortho position. And so we actually get para favored in that. So there are versions of teaching this material that really ask you to pay a lot of attention to those directing effects between ortho and para. But for the purposes of our class, I don't think that we care that much. So that is electron donating groups being activating and ortho-para directing. Electron withdrawing groups kind of do the opposite. So electron withdrawing groups we said are deactivating. They take electrons out of the ring. And then if we do our resonance structures, now the thing that we see is when we take electrons out of the ring, now the thing that's being bounced around is a positive charge. And so what we have is that these ortho and para positions now are getting this positive charge bounced around. And so those are the relatively electron poor carbons on the ring. So if these carbons, ortho and para, electron poor, the meta ones, relatively speaking, are more electron rich. They have more of a partial negative. Now again, it's not that we are directing extra electrons here. These are just the sites that are not drained of electrons. And that would be the meta position to our electron withdrawing group. So over here, we have another group that's withdrawing. So notice that this is really, really close to what we saw over here. Over here, we had NH2, and over here we have NH3 with a positive formal charge on it. And one thing to clock is that the difference here is the NH2 has a lone pair that it can donate, whereas the NH3 has no lone pair on here. And so it can't do any donation via resonance anymore. So all it can do is it's a nitrogen with a positive formal charge. That positive formal charge makes it even more greedy for electrons. It makes it more electronegative. And so it's going to withdraw electrons out of the ring by, well, what do we call that? When something's really electronegative and it withdraws electron density. Anyone recall? Electron withdrawing because of high electronegativity. Kind of like if we had a carboxylic acid and we put fluorines here. It would be the same effect. Induction. Ding dong. So that is induction, where we have something really electronegative that's going to tug at that electron cloud and pull some of the electron density out of the ring here. Great. Now, we also said it was deactivating. Withdrawing groups take electrons out of the ring, and that slows down the rate of a reaction. And one thing that Serena didn't really talk about here, and you are not going to be tested on it, but It's something I think worth mentioning, and it's something that we include for the summer version, which is that some of these withdrawing groups, like these acids, the nitro group and sulfonic acid group, they are so deactivating that actually there are some EAS reactions that can no longer proceed after you put one on a ring. So like if you have a nitro group on a ring, you cannot do Friedel-Crafts alkylation anymore or Friedel-Crafts acylation. Just because this is taking so much electron density out of the ring that this is now an even worse nucleophile. Again, that's not something that you're going to have to really take into consideration when you are doing things, but because it is part of the action and what happens, I wanted to mention it. So I've made a nice little yassified chart here, kind of giving you some examples of strong, moderate, and weak activators, and same with deactivators. And we see all of our activators are ortho-para-directing. And we see that most of our deactivators are meta-directing. But something's going on over here with the halogens. So halogens, we know, inductively withdraw via induction. I already said inductively withdraw. They withdraw electron density via induction, and we know that that's a pretty significant effect for halogens. We've seen that like have pKa effects in other situations. And the thing is, it has a lone pair, and so it can technically donate by resonance. But is this a good resonance structure? Does fluorine, the most electronegative atom, like having a positive formal charge? No, I don't think so. And so we do have resonance, but it's super weak. So when we ask what's the dominant effect, well, the dominant effect is induction, withdrawing. However, and because the dominant effect is withdrawing, we say it's a deactivator. It's taking electron density away from the ring. But given that, the other thing that we said is directing effects are controlled by resonance. So even if this is a really weak resonance donation, it is still resonance that would direct ortho and para. And so that is why the halogens are our only exception. And at this point, it seems that to get the sound effects to work, you have to manually on Zoom switch to the other screen. So if you care to hear my sound effect here, you can do that now. But to the halogens...
Darling, you are the only exception. You are the only exception. You are the only exception. You are the only exception.
Oh, I was like, man, it's going to keep going. But now you can flip back to the screen. Again, sorry that the effects are clunky, but here we are. So to give you an idea of how these kind of activation and directing effects work together, a very classic type of problem to encounter with EAS reactions is called a tri-substituted benzene synthesis, where you start off with a benzene, and then you add 3 things to that benzene. And you have to pick out which route is going to be best to get this product. And when we are doing that, we are thinking about things like activation and deactivation of our ring, and we are thinking about directing effects. So let's try to do this together. I wrote out literally every possible option that we could have done of like, which do we do first, which do we do second, and which do we do third. So let's try to think through these directing effects. So first off, if we had added a bromine first, well, what is bromine? Is it an ortho-para-director or a meta-director? Well, we know bromine is our only exception. We know it's an ortho-para-director. And so, our nitro groups and acetyl groups, are they added at the ortho and para position where we would want them to be to get our product? Well, yeah. One of them is added para, one of them is added ortho. And again, we don't really have a good way of controlling that right now, but right now, both of these seem like plausible options. Now, if we have our nitro group first, we ask, is nitro a orthopara or a meta director? Also, really quick, do people have the notes on Canvas, or are they not there yet?
I do.
Okay, cool. I only posted them like 10 minutes ago, and so if you're using it, especially on a tablet or something, you might just need to refresh. But, so if we had our nitro group first, we know the nitro group is electron withdrawing, so it's a meta director. So if we want to get our bromine and our carbonyl in the right place, could we get, I guess, how do I phrase this? Is this a meta direction to get this bromine where we want it to be in the product? No, it's not. And so we know that we can't have done this route of NO2 within a bromine, just because the directing effects don't match up. If we did have NO2 and we added bromine, the bromine would go here, not there. And that's not going to get us towards our product. Wait, are more people not getting access to the section notes? Okay, work. Okay. Then over here, this is one where, for the purposes of your class, this would be fine. But remember where I said that the NO2 group is actually super deactivating and it's going to shut down Friedel crafts? So this one wouldn't work just because it's deactivating. And so that's something that we like to think about, if we can. Again, I don't think that that's something you'll explicitly be tested on. But what this means is that these two routes are not good synthetic routes from making this product. Then over here, we look at the last one. So if we have a carbonyl, carbonyls are going to be electron withdrawing groups. So they direct meta. And now of these two, are they meta, where we want our thing to be in the product? Well, the bottom one works, but the top one, here, our bromine, we want to be para to our carbonyl. And so we are going to get the wrong arrangement if we add the carbonyl first. Then from there, we have to ask ourselves, okay, where do we add the second things? So over here, we have a bromine and we have an NO2. And we need to add on our carbonyl. What's wrong with this route? If we try to add on a Friedel-Crafts carbonyl onto a benzene ring from this starting material, well, our directing effects would actually line up. So for the bromine, it's going to direct ortho and para to it. For the NO2, it's going to direct meta to it. So it's directing to where we want to. But here, remember, if we have an NO2 and we're trying to add carbons with a Friedel-Crafts, this route's not going to be great because it's deactivating with that NO2 group. What about this one here? So our bromine, it's going to be directing ortho and para to it. So we have ortho, para positions taken by the carbonyl. And then we have our carbonyl that's going to be directing meta to it. Ooh, they line up. That's perfect. And hey, that's exactly where we want our NO2 group to be added. And in fact, if we add it to either of those two positions, we can just flip the benzene over and it's going to be the same product. So this route works. So if we first add our bromine, then we add our carbonyl, then we add our nitro group, that is going to be a valid synthetic route. So bloop, 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 bloop. And then maybe let's check this last one here. In this last one, we have the NO2 group and we have the carbonyl, and we need to add a bromine. And so our NO2 down here is going to direct meta to it. And then our carbonyl is going to be directing meta to it. And so that's not where we want our bromine to be. We want the bromine to be here kind of ortho to the NO2 group. And so this is going to have bad directing effects. So of all of the possible options that we could have done to add these three things on the benzene, only one route worked. And again, I think for the purposes of our course, we would have also accepted this one here with the deactivating And then this one, it would have failed also in the second step with directing effects. So I guess there would be 2 valid options for our course. But this is why this becomes such a common exam question for testing the EAS reactions, because it's making you think a lot about resonance and these directing effects and like the order in which you add things. And it's another way that a reaction family we've seen gets a little bit more complicated. So this kind of idea of like the order that we add things and the directing effects is something that we'll have to keep an eye on. With that in mind, let's look at some of these practices now. So, first practice, we have a couple of line reactions. So, let's start off by analyzing what's here. So here we have a nitrile, CN, and in the products, we're adding a bromine, and then we have, a carbon and a nitrogen. Does anyone have any ideas, like, how we could get this? Because that looks weird. That doesn't look like our EAS reactions, right? We didn't see one where we added a carbon and a nitrogen. Well, do you think that these are totally new? Or are these going from the CNN that are already there? Oh, sorry, there were a couple questions real quick in the chat, so I will answer them. So nitro groups are deactivating because they are literally taking electrons out of the ring. So here, like this resonance example shows it with like a carbonyl, how you see literally electrons are leaving the ring, making it partial positive. A nitro group, what it looks like is N double bond O, O here minus plus. So the nitro group here has a lot of electronegative elements. It has 2 O's and an N. So it's going to have a lot of inductive withdrawing as well as having resonance withdrawing. The second reason why it's even more withdrawing than like just a carbonyl is because when we withdraw out onto it, then what we are getting is a really stable resonance structure where we have 2 negative charges on oxygens. And so because it's such a stable resonance structure when we withdraw and because there's so much induction, it's taking a lot of electron density out of the ring. And with so much electrons leaving this ring, this benzene becomes a worse nucleophile. And so it can't do some of these like trickier reactions like the Friedel-Crafts reactions. The Friedel-Crafts reactions require the benzene ring to be a slightly better nucleophile and have more electron density. And then, Gabrielle, to answer your question, moving forward with box and line reaction problems, yes, for benzene rings, if you see that in line reaction problems, you are definitely being asked to consider directing effects. Yeah.
Can I ask one more question really quick?
Sure.
So along those same lines with that same question about activating, deactivating.
Yeah.
So with your chart that you have, that is the beautiful substituent effect summary chart up top. So when nitrogen, so the bottom row, so it's nitrogen with either oxygen, 2 oxygen, or 3 hydrogen, and then nitrogen essentially with anything else like paired up top as an activator. Is that right?
And the difference is there a lone pair?
Oh, okay. I missed that. Thank you.
Pair, totally. Then it's a donor. But over here, this nitrogen has 4 bonds, 1 to the ring, 3 to H's. And then this nitrogen has 4 bonds, 1 to the ring, 3 to O's. And so because of that, 1, they have a formal charge, so inductively withdrawing. And 2, they don't have a lone pair. They can't do resonance donation. And so that is why they are so deactivating. Yeah. Good questions. Okay, so back to her. Has anyone ruminated on this a little bit more? Have we thought, is she going to be brand new or is she connected to the nitrile here? And if someone thinks they have an idea, what reaction is coming to mind? Fallon, I like where you're thinking from the CN that's already there. So do we know a reaction that takes a nitrile to a primary amine? So close, Sarah. So close. So we only really know 2 reactions with nitriles. One is we can add H3O+, and that's going to turn into a carboxylic acid. So it's going to get rid of the nitrogen, which we don't want. And so our other option is reduction. So we know that we could do a lithium aluminum hydride situation, and that's going to change it into this substituent here. So now we know that we're adding a bromine. So we know the reagents for bromine are Br2 with FeBr3. And also, can someone remind me, did Serenia actually use FeBr3 or did she use AlCl3 with Br2?
So I had a question about that. I swore I've seen both, but maybe she only used one. I don't know if anyone else also got confused about that.
Let me check the notes, but if someone can find it faster or has a memory of it. Yeah, I'm looking at page 11 of the notes, and she does use FeBr3. And then for chlorine, she uses FeCl3 instead of AlCl3.
Can you use both for chlorine, or does it matter?
It doesn't really matter. Like, it's just Lewis acid. In the summer version, we don't talk about them being interchangeable, but they are interchangeable. And so the little mnemonic I use is like, BR2 is like, bruh, I'm pumping iron at the gym. Bruh, iron. It's dumb, but here we are. Especially since they're interchangeable, it doesn't matter. Okay, so we know that we're doing this. And so the thing that we have to think about when we're doing line reactions with benzenes now is directing effects. So if we have the CN like this, is this CN, which I'm actually going to draw out, is that going to be a withdrawing group or a donating group? The question is a nitrile electron withdrawing or electron donating? Withdrawing. And the way it works is we have a pi bond adjacent to a ring. So what is going to happen is electrons can go out and push up just the same way as if we had like a carbonyl. So because this is an electron withdrawing group, we know that it's going to be a meta director. Okay. Over here, if we have a carbon and then an NH2, is this going to be an electron withdrawing group or electron donating group? Does the lone pair on nitrogen not make it an activator? So, we only care about the lone pair if it is right next to the ring. So like here, the lone pair is right next to the ring, and so it can donate in. Even though, remember, chlorine was the exception of the halogen where it's a little bit weird. But here, this cannot donate straight in because this carbon is sp3 hybridized. It has 4 bonds, and so we know we can't do resonance with it. But that means if we have like an sp3 carbon right next to the ring, this is really acting kind of like an alkane. And alkanes, we said, were good donors, or were okay donors, I guess, via hyperconjugation. So this one is going to be an electron donating group. And it's going to be an ortho director, orthopara. So what is the relationship between our final products of this carbon-nitrogen thing and the bromine? Well, the final relationship is actually meta. So if we want meta direction, what we need is we need to have our nitrile in place when we add the Br2 FeBr3. Like essentially all of the things that we were doing is we knew just from looking at like discovering that we were doing LAH things and here adding a bromine, we knew the reagents, we just didn't know the order. But so now that we've thought about our directing effects, we know that the order has to be 1, add in our bromine. Then 2, we add our lithium aluminum hydride with ether and acid workup. And so the reason why we had to think through our directing effects is because if you had done it in this order, and actually I'll just copy the whole thing. So if you had first done the reduction and then done the bromination, then the product that you would get out would put the bromine ortho to it, or ortho or para to it. So essentially it would just be in the wrong place from where we would want it to get this product. So this is just kind of for comparison here. Okay. Now, the second one here is going to be a classic trisubstituted benzene addition. So we know that we need to add a chlorine, we know we add to a sulfonic acid and a nitro group. So, I mean, I can just go ahead and write out the reagents. I know we need HNO3, H2SO4. I know we need SO3 and H2SO4. And this is sometimes called fuming sulfuric acid, which is, again, kind of fierce. And then Cl2, AlCl3. Only question is which order we should do. So, a good rule of thumb and a good thing to try, because doing all of the possible routes, that takes a lot of time, and you don't want to have to do all that. But a good rule of thumb is first add your activating things or more activating things, and then save your more deactivating things for later. So our strategy: add strong deactivators last. So given that, we know our nitro group and our sulfonic acid are going to be strong deactivators, so let's try adding our chlorine first, just to see. And again, it's a lot of kind of trial and error doing the process. So here, if we've added our chlorine, then we know chlorine's going to ortho-para-direct. And we see, okay, well, these two things that we want to add are in ortho-para positions. That works. Okay, now we can just try adding one of the other ones. So let's try adding like SO3H. So if we do that next, we have our chlorine, and then here, SO3H, we can add it para, and that agrees with our ortho-para directing. And now, our SO3H directs meta to it, and our chlorine directs ortho to it, since the para is taken. And hey, that lines up for where we want our NO2 to be. So we can do NO2 third. And actually, I think the order of these two doesn't particularly matter. I like doing the para position first, just because there's less chance for sterics. Like a sulfonic acid group is fairly large. And so because it's fairly large, the sulfonic acid group will probably add more to the para position than it would to the ortho position. But there we are. So that's kind of like the hard part's not remembering the reagents. It's really just thinking through the kind of order of things, and there can be multiple acceptable answers here. Like for this one, we could have swapped the order of these two, and that would have been fine. Then let's take a look at mechanism. I don't like the look of this at all. So, again, when stressed, we fall back on our strategies of spot the difference. We go from a benzene to a benzene with two things added to it, right? One of them here appears to be a Friedel-Crafts acylation. Remember, acylation is what we call it when we add a carbonyl in its R group. And hey, this reagents that we're using seem like classic Friedel-Crafts acylation reagents. So that kind of makes sense to me as something that we could add. But then this one over here is tricky. So this one over here looks like a Friedel-Crafts alkylation. Like we've added an alkyl group. It looks like it could have gone from this tertiary carbocation. Whereas our Friedel-Crafts acylation, we know that that reactive intermediate is going to be our carbonylid, which again I think has a fancy name that I'm forgetting it. So, interesting. This is what we would expect our electrophile to be, both for the reagents given and for this part of the product. And yet somehow we need to be able to get this carbocation. More than that, what is the relationship between our two groups in the product? Are they ortho, meta, or para? Well, here they're across from each other, so they are para. So, which group did we add first if these are para to each other? Did we add our alkyl group first? Or did we add our acyl group first? Since they are para to each other. Take a minute to think it over. Which should we add first? The alkyl group or the acyl? Since they are para to each other. Does that feel like too hard of a question right now? Like, part of me is also like, this is new for y'all, and so I'm like, they might be asking a little bit too much all at once. That's, yeah, y'all are still getting it. Mm-hmm. So, our relationship across the ring, just for para, to recap that, is if they are like 180 degrees opposite of each other, then we call it para. And so here, these are exactly opposite each other, so it's para.
Colton, can I ask a question? Is that okay?
Yeah.
So, okay, when you're asking us this question, my thought, I looked back at your pretty chart you had, and seeing that whole group that would be added, it's an M director. Mm-hmm. So that was my comment. So I just didn't understand, you know what I mean?
Yeah, you're thinking about the exact right question. So, like, really what I'm asking is did we first do this and then we add this? That's option A. Or option B, did we first do this and then add our carbonylid thing? And in order to answer that, we need to know the directing effects of each of these. You are totally right that this thing right here is a meta director. So if we added that first, then our product that we would get would add the alkyl group meta, which is not our product. In our product, they are para. And so we know that route B has to be the order that these happened in. Here we have an alkyl group. Alkyl groups are ortho-para directors. And because it's bulky, it's not really going to direct ortho. It's only going to direct para because our R group is so bulky. And so we know if we do the alkylation first and then add on our acyl group, that is going to give us the right directing effects. So, and again, it's kind of this thing of like you have to imagine what it would be like if we did one option first versus the other. And I think when you're starting out, doing little drawings, I think is actually really helpful. Just to like check yourself of like what's the reality of what would happen. I think once you get to the exam, you want to get to where you can kind of imagine some of these, or maybe just draw one of these instead of the whole pathway. But I think it's really good for it kind of thinking through strategies. So somehow we know that we need to add this kind of alkyl group first, but we don't really know how we're going to make this. This thing, the other thing I kind of will say about it as we're trying to piece it together, it looks awfully similar to this like tert-butyl group, right? Like that's 4 carbons with that same arrangement. So I'm wondering if it seems like there needs to be a weird step that happens where essentially this whole thing leaves. We have one other hint. And maybe I'll make this green as we're kind of like the mystery of what happened. One other hint is that carbon monoxide gas leaves. Huh. Let's see what's going on. So, to start off, and actually I think that the Lewis structure for this would be like a minus plus situation. It's been a minute since I've done carbon monoxide's Lewis structure, but let's start off the way we would start off for our Friedel-Crafts acylation, because like that's the reagents we have. So for Friedel-Crafts acylation, first thing that we would have is the alkyl chlorine is going to associate with the AlCl3. Going to donate into the aluminum's empty p orbital, and the aluminum acts as a Lewis acid. So then what we have is a minus on the aluminum, plus on the chlorine. And what we would expect to happen under Friedel-Crafts acylation, we would expect push down, kick off. So that would get rid of this AlCl4. And then we have a CO triple bond. And then we have our electrophile. So that's fine and well, but that's the electrophile for our acylation. And we are trying to get a carbocation like this. So any ideas of how we could go from what we've done so far to our carbocation? Going from here to here. How have we made carbocations in the past? Well, if we were trying to go from here to here, where is the nucleophile going from here to here? Did nucleophile enter the... Yeah, nucleophile didn't enter the picture. So how else have we made carbocations in the past? Think like SN1. What if the leaving group just leaves? Bada bing, bada bang. We've kicked off CO, gas. And we have a tertiary carbocation. But wait, why doesn't this happen with every acid chloride? Like, let's say we did it with Cl like this, and we did steps and we got the here with a methyl. Why doesn't this just leave? And we get the CO gas, and then we have a methyl carbocation. Oh, so CO, we have not talked about it being a leaving group. The thing that we know, the reason we know it's left is because they give it to us here. It's also the thing that, like, anytime a gas leaves a reaction, that's a big thermodynamic driving force for the reaction. Like, it drives the reaction forward via Le Chatelier's principle because the gas bubbles out of the mixture. But why does this not work? We want it to be a stable carbocation, or like a tertiary carbocation. So that's exactly right, Fallon. So here, this weird step of this CO leaving group leaving only happens in the case of this reaction because we have a tertiary group on the side of our carbonyl. It's not going to happen with any other groups on the side. Great. So now that we have our good electrophile, our benzene can come in and we do our first EAS step. So all this in blue first was making our Friedel-Crafts alkylation electrophile. And then we do EAS number 1. So our benzene ring is going to come along. And then blah, blah, blah. It's going to go and attack the carbocation. Now, when we do that, we have our group added, but that position also has a hydrogen that was already initially there. And we have a carbocation created over here, plus. So now we need to restore aromaticity, so something in our solution is going to deprotonate it and fold back in. And let me see what Serenia used for this. So she likes to use specific molecules for it. And she used, instead of Sol, which is just kind of generic for something in solution, she used actually the AlCl4. So this sigma bond here, kind of like AlH4 sigma bonds attacking, this is going to go and grab an H and do this kind of E1 elimination. That's going to spit off HCl and AlCl3. And then we are at our intermediate here where we've restored aromaticity. We've added our first group on. Okay. Well then, for forming our electrophile number 2, or Friedel-Crafts acylation electrophile, we use the exact same steps that we had before. So I'm going to copy and paste this. And I will put it, I'm going to minimize this. This is making our Friedel-Crafts acylation electrophile. And we just are not going to have the leaving group leave. So now, at this point, the benzene ring down here is going to go and attack our good carbon electrophile in this acylation intermediate. And we know it's going to add at this pair position because this alkyl group is going to be orthopara directing. So this is EAS number 2. So our tert-butyl up there is unbothered. We already had a hydrogen on this position, so now we add our acyl group. And then we have a carbocation that was created. And then yet again, our AlCl4 is going to come and do this E1-like elimination. Actually, I think it is straight up an E1 elimination. So that's going to spit off an HCl and an AlCl3. And then we get our product with aromaticity restored. Woof. So we can see how the mechanisms for this can be a little bit trickier and also adds more of a conceptual element to it than I think a lot of the other ones in this unit. So like substitution elimination is kind of its own thing with the GFP system. With alkenes, we're having to think about stereochemistry a lot more. And then with like the EAS family, we're having to think about directing effects. That's going to be the bigger one, and making these good electrophiles. Cool. Any questions on this? Okay. So the other main topic in Lecture 9, other than the EAS reactions, was aromaticity. Now, for aromaticity, I'm about to present y'all with options. So, aromaticity, in my opinion, is actually one of the slightly easier topics. And it's one that I normally skip in section in favor of talking about some study strategies with y'all. So, I have a YouTube video that I've made that's like a 15-minute video that like does my spiel on aromaticity, talks through some examples of aromaticity. So, option A is I do a very, very, very light touch of aromaticity. Like spend like 2 minutes on it, and we do practice number 4, which is not in the video. And then we move on and talk about how to study reactions and some strategies here. So that's option 1. Light touch of aromaticity, move on to study stuff. Option 2 is we do a in detail talk about aromaticity, and then we do a light touch on the study strategies. Which would y'all prefer? Light aromaticity, heavy study, heavy aromaticity, light study. Now that I know that y'all have to switch to the other one to hear the sound effects, it makes it not worth playing the Jeopardy music while I wait for y'all. So I'll just do 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 do. So right now we have 3 for light aromaticity, heavy study, and then 1 for heavy aromaticity, light study. And we have half of the Zoom viewers not voting, abstaining. I feel like at least right now I have to give it to the light aromaticity folks. But we can revisit that if more votes come in, some absentee ballots. Cool. So little light touch of aromaticity. It is a phenomenon, a chemical phenomenon, where when we have a conjugate ring, it is unusually stable. Like more so than you would expect from something that's not a ring. So imagine this, we would call this 1,3,5 hexatriene. So this is kind of like a straight chain. You could also think about like this straight chain version of it, but I've just kind of folded it to look really similar to a benzene. And imagine this versus benzene itself. Benzene is way more stable. And it is like an ungodly amount of energy difference between the two. That like really we have no other way of explaining it before we knew what aromaticity was. It is about 36 kilocalories per mole that is gained through aromaticity. Whereas conjugation, just general resonance that we've talked about in the past, it's like 2 to 5 kilocalories per mole. Like that's the normal amount of stabilization we would expect. Aromaticity, like more than pentuples it. So something is going on where it makes the compound really unusually stable. It's also the thing that like this 36 kilocalories per mole, for reference, ATP hydrolysis in cells only yields 7.3 kilocalories per mole. So like this is like multiple ATPs worth of energy difference in aromaticity. And I like to think about the electrons when you have the conjugation here. We said that electrons could flow freely between the p orbitals, but when they're also in a ring, I imagine the electrons get in a little hamster wheel and they just keep running and running and running and they're really happy. Or like, you know the little dog treadmills that they have where you can like hook the dog in and the dog realizes that they can run as fast as they want and like they're very, very happy. That's kind of what I imagine the electrons are going through with aromaticity. So, we have 4 criterion for making something aromatic. It needs to be cyclic, it needs to have continuous or contiguous p orbitals, it needs to be completely flat and planar, and then the last one, the kind of weirdest like property of it, is we have to have a Huckel number of pi electrons. Yeah, I think Saridia said like Huckel, And I was like, no, this man was German. It's Huckel with a mixed vowel. And so, again, these Huckel numbers are the numbers generated by the pattern 4n plus 2. So you can plug in n of 0. 0 times 4 plus 2 is just 2. You can plug in 1. 4 times 1 plus 2 is 6. You can plug in 2. 4 times 2 plus 2 is 10. Plug in 3, so on. So if you want to just remember these numbers for the first ones, you can just memorize them, or you can memorize the pattern. And so if I told you that there were 4 pi electrons, we can't write 4 as 4n plus 2, where n is just a whole number. Like, so this would be a non-Huckel number, and it would not satisfy this fourth property. So when we have a compound of interest, if it satisfies all 4 of these properties, aromatic. If it satisfies 1 through 3 but not 4, then it's kind of like was so close to being the superhero becomes the supervillain. It becomes something that is called anti-aromatic. And that is like the exact opposite phenomenon of aromaticity, where a molecule exhibits unusually strong destabilization because it's cyclized and has all this relationship. And so I almost kind of think again about this reciprocal idea of like, if we have bonds, we have antibonds. If we have aromaticity, we have anti-aromaticity, where it's very destable. Molecules will do a lot to avoid being anti-aromatic. So, again, if it satisfies all of them, it's superhero. It's aromaticity. If it satisfies the first 3 but not number 4, anti-aromatic, the villain arc. If it just fails one of these other ones, then we just call it non-aromatic. Like, it just kind of doesn't apply. It's not close to being the superhero or the villain. It's just Joe Schmo. And to give you an idea of how badly anti-aromatic things don't want to exist, we can look at cyclooctatetraene. So, cycloocta, an 8-membered cyclic ring, tetraene, 4 alkenes. So, in this arrangement, it is 1 cyclic, 2 has continuous p orbitals, 3 appears to be planar, but then it has 2, 4, 6, 8 total pi electrons. And so with 8 pi electrons, that's not one of our Huckel numbers, so it would fail number 4. So this thing, if it was flat, it is going to be anti-aromatic. So what it does is it literally puckers the whole molecule to make it not flat, so it fails number 3 and just becomes non-aromatic. And like, this thing is strained. This thing is like very uncomfortable. It does not want to adopt these bonding positions, but anti-aromaticity is so like dramatically bad that it drives this molecule to take on conformations in order to make it simply non-aromatic and not anti-aromatic. So, again, more talking about this in the video, more practice about this in the video. There are 2 kind of quick conceptual questions I want to do, which we could spend a lot of time talking about these, but I don't really want to. We can use aromaticity to explain things. So this first one, we are asked, why does this molecule have a strong dipole? Well, as this exists, these electrons are not in a ring. They are outside of the ring. And so when we're trying to count like the number of pi electrons in these rings, these are this weird ambiguous case. This is what's called an exocyclic pi bond, which I have a little infographic about if you want to read a little bit more. We're not going to like heavily test you on it or anything. But basically, we need to decide where these electrons live. Do they live in the left ring or the right ring? So we hypothetically can have 2 versions. One where the electrons hop over to the right, one where they hop over to the left. So in our green version over here, the negative charge goes to the left, and on the right side we have a carbocation. And that tracks with what they said of forming a dipole, like a negative charge and a positive charge. And then our blue version, now, in this version, the negative charge went over here, the positive charge went on the 5-member ring side. Well, obviously, this is planar. Obviously, it's continuous. Obviously, we have 2 rings here, so these rings would be cyclic each. But then we ask ourselves, how many pi electrons do we have in each one of these? So in this ring, when our negative charge, our like a lone pair, is on the 5-membered ring, we have 2, 4, 6 pi electrons. And then over here, we have 2, 4, 6 pi electrons. Okay, well, that's one of our aromatic numbers, our Huckel numbers. So these are both aromatic if we form a dipole out of these and make the negative and positive, that charge split. But over here, when we do it this way, now this ring only has 4 pi electrons and the other ring has 8 pi electrons. In this case, both of them are anti-aromatic. So the molecule is not going to form a dipole like this, and it will form a dipole like this in order to create these 2 very stable aromatic rings. The other one, why does this molecule have an unusually acidic proton? Well, again, we have this thing that we've seen. If we can put the electrons here, like I'll go ahead and draw that, then we form an aromatic ring. And anytime we have the chance of forming an aromatic ring, the molecule is going to do whatever it can to do that because it's so stabilized. So, how could we combine this with this idea of acidity? Well, if we think about over here, like trying to do this resonance structure, where here we have a carbocation, here we have the negative here. We know that a molecule with a carbocation is not super stable, right? So what if we could do something to get rid of a carbocation? And again, we're thinking about acidic protons, so we're thinking that we're in a base solution. So what if we have a base come along and deprotonate at this position 1 away? Well, then the electrons in here can fold in, and then we can push our electrons into the ring like we want. So if we deprotonate it, what we form is a ring that looks like this. So we've created an alkene on the end doing like an E2-like elimination, and we've created an aromatic ring. So again, I think that if you see something that's a conceptual question on the test and something looks close to an aromatic ring, be thinking about what things, what behaviors might this molecule do or ways that it might react in order to become aromatic, because it is such a strong driving force. And with that, I sadly need to move on so that we can talk about things. So, I normally have this into 3 sections. We had How to Study Reactions Part 1, and I think Lecture 4, when you had your first reactions, and we talked about thinking at reactions at different levels of depth. And then I normally have Part 2 and Part 3 for the summer class, but I'm going to be doing kind of both of these together. And I'm going to start here with this idea that, like, with exam 1 and 2, with exam 1, it was really just like, here are a bunch of different disparate skills. Exam 2 was kind of like, here are your first sets of reactions, and those were kind of the big challenges. But the challenge for exam 3 is we now have like 60 plus reactions that are all going to be fair game for the exam, because exam 3 is going to cover all of lectures 1 through 9. It's going to pay more attention to this most recent batch of lectures, but especially for things like line reactions and box problems, you are going to need access to all those old reactions, just like we saw today with that nitrile hydrolysis. So, the general types of questions that you're going to see on exam 3, and I don't have an exact layout, is really what you saw in exam 2. You're going to have line reactions, and I'm willing to bet 1 page of those line reactions is just going to be substitution elimination of like which happened, which option. You're going to have mechanisms, and then you're going to have these kind of theory, reactivity, other kind of miscellaneous mechanism thinky questions. This is going to include things like, is it aromatic? It's going to include things like directing effects. And then I'm trying to think of what else. It could also do something like SN2 or SN1 speed of reaction. So theory questions about like leaving group ability or about sterics or something. But that's kind of the general breakdown of it. And a majority of the test really is going to be these reaction-based line reactions mechanisms. So I think a couple of goals when you're studying here are going to be, one, try to get through the P-sets as quickly as possible so you can get into your kind of dedicated study time for the exam. We're going to have our last lecture for the course on Thursday. And to be so honest, I actually don't know when P-set 10 is going to be due. I don't know if it's going to be due before exam 3 or after it or whatever, because we don't have anything next week. We don't have lecture, we don't have section or office hours. And so we're going to come back after Thanksgiving, and we're going to have one more section that's going to be the like mini exam, like we've done before all of the other exams. And then after exam 3, I think we'll have a final section that's like section 10 stuff. But a first goal being, whatever problem sets there are, try to get through them as quick as you can so that you can have the dedicated reaction study time. And then the second goal, I would say, is try to get most of your reaction basics down by Thanksgiving. So by like next Thursday. And my favorite strategy for getting the basics of a reaction down are this exercise that I call the Desert Island exercise. So you all already have studied for one exam, and so you've tried out some study strategies for learning the basics of reactions, and I think exam 2 has let you know how effective your study strategies were. So you've already gotten some feedback on what you are currently doing and how well it's working for you in terms of getting those basics of a reaction down. But I really like this strategy, the Desert Island exercise or DIE drills, just because I think that they are quite time effective. So the setup is, on a blank page, write out the starting materials of a reaction that you want to study, exactly as they appear in your lecture notes, and then put everything away. So this is an old reaction. This was like an exam 2 reaction for y'all. This is the amine reaction. So I've written one of them just from lecture notes. And the basics of a reaction in my mind are being able to very quickly, within like 10 seconds, draw what the product should be. And then within about a minute or two, draw the full curved arrow mechanism. And so what I'd like us to do is I'd like us to actually do one of these drills to see. So if you could, either on your iPad or on paper or something, get kind of a blank page and write this out first. So what we are going to do is we are going to set a timer for exactly 3 minutes. In those 3 minutes, I want you to try to predict what the product is and write a full curved arrow mechanism. Then, once we have done it, we are going to stop and we are going to grade ourselves and give ourselves feedback. Like switch to a red pen or a red little marker on your iPad. And this, I think, is going to be helpful for diagnosing what is on lock solid in your head versus what is like a sticking point for you. So I am going to start a timer up, and I'll do the exercise as well. So are people generally ready? Can I get like a yes or a thumbs up or something? Okay, we know what we're doing, drawing the product and then the mechanism. So I'm not going to be able to show the timer because I am also doing my screen here. Or actually, I will show a timer. Are you mark? Get set. Go. to pause the screen share because I'm going to try to do it in a minute. Hey, we did it. Okay. So, take a minute, check your work. And the other way that you could have done it, alternatively, I'll put it up here. You could protonate this first. And then from this structure, then you could do your proton transfer and then take it to water. And then NMEH. And that would be the same as up here. So take a minute and like grade yourself on each of the curved arrows and everything. And your intermediate structures. We have formal charges, all of that. And this is the thing, because it's a reaction that you've already been tested on, this might have been super easy for you. But I bet if I asked you to do the same thing with a Friedel-Crafts reaction, then that would probably be a little bit more of a challenge, right? But I think a lot of students think of this as a test for you to do when you have already studied your reactions. And what I would kind of like to propose is that actually this is a tool that you can use in a time-effective way to learn your reactions. Because if you get stuck at a step, you will know by doing this. Like, you will try to do it without something there, you will pause, and you will not be able to continue. Or, like, if there is a step that has gotten messed up somehow, this really helps in a time-isolated way. It helps you diagnose what is going on with your thinking. And it also helps you think about, okay, maybe I got it correct, but it took me 45 seconds just to figure out what to do here. In that case, that to me is suggesting that we don't know why this is happening in the grand scheme of the reaction. And that can point that out to us and make it easier. And this is the part one is kind of the basics, and then we can generalize it. So then do the same exercise with any amine, with primary amine, and with any ketone or aldehyde. Then try to do an intramolecular version where they're on the same molecule. Then try to do it the reverse reaction where you start with an amine and break it apart and go backwards. I really, really like this because one, it's active learning. The whole time you are having to think, and it's not like a flashcard where you don't really have to do anything active. It can be very passive. And it's also not like, what's the other one that people use a lot? Just copying a reaction out of your textbook. Here you're actually having to kind of think through it and derive it again on your own without anything in front of you. I like the time strain because it doesn't let you turn your gears forever. It really makes you kind of focus on it for a little period. And then it's also something that's really flexible. So if it's a reaction that's longer and you keep getting lost in the sauce on it, then you can do dyes 8 times until you get it correct. But if you do it and it's a shorter reaction or it's easier, you only need to do 1 or 2 of them. Maybe do 1 or 2 of the direct ones that you saw in lecture, and then get onto this generalization to kind of extend this and see if you can do it with any version of that functional group. And so it's really just a tool that I find to be very, very pragmatic for taking in new reactions and learning the basics of, can you predict the product and can you do the mechanism? So that's one strategy I want to introduce. I know we're pretty much at time. I'm going to take 5 more minutes, if that's okay. So the other thing I want to say is with your studying, there are essentially a few issues that you have to engage with. One is a tractability issue. So if you just make a list of your around 60 reactions, it's going to just take too long. And also it's going to feel kind of overwhelming and there's just not a structure to it. So something in your studying must organize and condense these reactions. And what I use for that is I use reaction families. So thinking about all of the reactions as having their own kind of little web, or like if we think back to the reaction summary chart that I made for lecture 4, these are the kind of little families that we saw in lecture 4. And so I would divide that up for all of the lectures of like what families of reactions exist here and kind of clump them together so that instead of thinking about one list of 60 reactions, you're thinking about like, oh, okay, I have to get to know about 8 or 9 reaction families. So I think that tractability, doing something to organize it, is helpful. The other one is an issue of integration. Basically, I think that y'all get into a place where you get really good at one lecture and like doing things within one lecture. But if we ask you to bounce around between different lectures of reactions, it is less comfortable for y'all, let's say. So a couple of strategies that work on this integration issue that I really like. The first one I call a nature walk. So in a nature walk, chemical nature walk, you start with a small molecule and then you just turn it into something else and just keep going. So I said, okay, let me just reduce this. I'll use soft boy, NaBH4 with MEOH. Now it is an alcohol, and we're going to have both versions. Okay, what can I do with an alcohol? I can make it into a better leaving group. So I can turn it into, let's say, a bromine. And again, we have both versions with PBr3. Okay. Now that I have a leaving group, I feel like maybe let's do a substitution. So what if I add like NaCN? Okay, that's going to go back and do another inversion. Now we have a CN on here, plus minus. And ooh, actually, I did all this kind of plus minus stuff, but this thing isn't a stereocenter, is it? We have 2 methyls. So if I want to think about stereochemistry, I can just make one of them an ethyl. And then I see, okay, what can I do with a nitrile? Well, we just saw we could do a reduction of a nitrile, or we could turn it into a carboxylic acid. Maybe I'll turn it into a carboxylic acid, H3O+. And then here, now we have an OH. And then just like keep going and see, okay, now a carboxylic acid, what else can I turn it into? And the thing I like about this is it really asks you to kind of think between lectures of like, how are all of these things created? And it also puts you in a more creative space and a less fear space around these reactions. So I love a little nature walk as just kind of a study activity. And it's also the thing where you can think about creatively, like, okay, what do I want to turn this molecule into? And then like, do I know the reagents to get there? Or like, do I know the mechanism? You could do a mechanism nature walk like this. I would stick to concrete mechanisms. Second strategy is, do you have friends? Ideally friends in this class. If you do, find a friend and try to write a mechanism question for each other. And for the mechanism question, all I want it to be is 2 back-to-back reactions. So like maybe I would take something like here going from, I'll take it from the one I just did. So this bromine to this cyanide to this carboxylic acid. And you can think through those reactions on your own. You should write it out, the full mechanism on it as you're making it. But then what you present to your friend is you present you present the line reaction. So you would just present bromine. You would do 1, the NaCN, and then 2, H3O+, and you would put the product. And you would ask your friend to do that mechanism as if it was like an exam mechanism question. And then you would provide with them your answer key as well. And then suddenly y'all are getting more practice where you're having to piece together these reactions. If you hate your friend, you can give harder reactions, or you can do more reactions than just 2. So, friend mechanisms I also really like. The last one, which I won't spend a ton of time on, but it's one of my favorite strategies for organic chemistry studying, is reaction webs. Y'all did one of these with like one of the section notes where it was like a really complicated web, and I only want like spoken wheel like reaction webs where you put one functional group in the middle and you ask what are all the ways I can make that and what are all the things I can do with it. So like ways of making an alcohol, I could like reduce a carboxylic acid or an aldehyde with LAH, and I should write all the full reagents, but just to save time. And so I might also label these functional groups just to put them here so we see it. Another way I could generate an alcohol maybe would be from like an ester. And I could do an ester hydrolysis with like H3O plus or NaOH H3O plus. That would generate this alcohol. And then what are all the reactions I can do with it? And then go through that and like go through and try to make a comprehensive list from multiple lectures to integrate all those reactions together. And I put some like little webs here, but I like these isolated webs with just one main central functional group just because I think it's a little bit easier and more wieldy than one where you're doing a bunch of functional groups connected and you're making a big, huge map. But I kept y'all far too long. For those who've stuck around, thank you. I hope this was helpful to talk through some of these strategies. And then I will stick around for questions and for office hours in a minute. So I'll go ahead and stop the recording.